Okay, let's get started. I'm here to introduce the annual Clay Postdoctoral Fellowship Colloquium. This is one of the events that many of us, especially myself, look forward to greatly each year. I'm going to start out a little bit talking about the Clay family. And at the outset, I have to note that the Clay family is unable to be present today, very much to their regret, because Landon was taken ill and is unable to join us. So we were expecting Landon and Lavinia, his wife, and his oldest son Thomas, and Thomas's wife, but they've sent their regrets. They have attended, at least Landon and Lavinia have attended every other Clay Fellowship colloquium since the inception. The Clays are prominent philanthropists. Landon made his money in finance, and has a number of philanthropic interests. Actually, his number one interest is not astronomy. His first love, which he'll tell anybody who speaks with him, is mathematics. And he endowed and supports the Clay Mathematics Institute, which is located in Cambridge. He also established the Clay Mathematics Prize, which is $1 million. It's a very significant incentive to solve one of the great classic mathematics problems. But he has been nevertheless very generous to his second love, which is astronomy at the CFA. He made possible Harvard's joining the Magellan Telescope project. So the fact that we have access to 20% of the nights on the twin Magellan telescopes is in large measure because of the Clay gift. And as a result, the second of the two Magellan telescopes is known as the Clay telescope, as those of you who've used it will know. He also established the Clay Fellowship, which we award annually, and is our premier fellowship here at the CFA. And he also gave $3 million at the very beginning of the Giant Magellan Telescope project, when a small subset of the current partnership decided to try and just cast one of the mirrors and polish it just to see if the mirror could actually be made. Because an off-axis mirror to those tolerances and that scale had never been built before, manufactured before. And so that was actually the first philanthropic gift to the Giant Magellan Telescope across the entire GMT partnership. And it helped us get that first mirror started and ultimately finished, and retired the greatest technical risk in the GMT program. So the family sends their regrets. They will have to watch you on YouTube. So let's turn to Kate. Kate started out in Ithaca, New York, and was educated at Yale and at Santa Cruz, where she worked with, I guess, Jason Prochaska and Dave Koo. Yeah. She went on to Heidelberg for a first postdoctoral position, and was awarded in 2011 a Humboldt Fellowship. But she's been with us since 2013, and we're delighted that she's here, and I'm looking forward to the talk, which is Gas Flows and Galaxy Evolution, The Wake of the Giants. I notice there's an S missing on the program, but what the heck. Right. Thank you, Kate.
Thank you so much. You all today. Thank you so much for coming. And I also am especially honored to have this opportunity to share what I've been working on, what I've been thinking about with the members of the Clay family, if not in person, at least via video. And I hope that it's clear by the end of my talk that I really consider it a great privilege to be able to work on and think about these issues for a living. So I'm going to here today summarize what we know about the distribution of diffuse gas in galaxy environments. And I'm going to focus on galaxies at redshift 2, when the universe was only 3 billion years old, of course. And I will show you, of course, some of my own work, and I just wanted to mention my collaborators on that project. My primary collaborators are Rob Simcoe, Xavier Prochaska, Joe Hanawi, Adam Myers, Neil Crichton, and Swinburne, and Simeon Bird. So everybody knows there are a lot of stars out there. Our galaxy alone has about 300 billion of these stars, and together they make up a mass of about 100 billion suns. So that's quite a lot of material. But of course, our galaxy isn't the only galaxy out there. This is the deepest image of the sky ever taken. It's the Hubble Extreme Deep Field. And I have included this just to demonstrate how much more there is out there beyond our own galaxy. And in fact, in this image, one can identify galaxies which are likely present only 400 million years after the Big Bang. And we estimate that in total, there are about 100 billion of these galaxies out there. So if you add up all the stars, all the 300 or billions of stars in these billions of galaxies, of course, that adds up to a lot of material. Now, these stars are made up of normal matter, of course, protons, neutrons, etc., our favorite kind. And we can get an independent estimate of the amount of this normal matter, the total amount of normal matter in the universe, by observing the cosmic microwave background. And so that has been done most recently by the Planck mission. And so we now know the total energy density of baryons in the universe. And it turns out that when we compare the amount of that normal matter to the amount of matter in stars, it's only a tiny fraction. Stars make up only 6% of all the normal matter, or baryons, in the universe. So where is all the rest of that stuff? Well, sometimes we can find it when we get lucky. We can observe bright quasars, bright light sources on the sky, like quasars, which are active black holes at the centers of massive galaxies. And if there happen to be some diffuse clouds of gas between us and those bright light sources, we can take a spectrum of that quasar, and the signature of those foreground gas clouds will be imprinted in the quasar spectrum. So this is just showing you an example demonstrating that process. This is the Lyman alpha line arising from neutral hydrogen in the rest frame of the quasar. And these gas clouds absorb light in their respective rest frames at the Lyman alpha transition as well. And so we can repeat this experiment and add up, just count all of the neutral hydrogen atoms in diffuse areas of the universe in this way, and we can account for about 40% of the normal matter in this diffuse state, what we call the intergalactic medium. But that leaves 50% of the baryons that we haven't yet counted. Now, we expect that a good fraction of the remaining material is probably close to galaxies. Galaxies, after all, form at the peak of dark matter overdensities in the universe, and so we expect that maybe some of the diffuse baryons are joining the galaxies in those peaks. And so to go after those environments, we need to take a slightly different approach, and this is an approach that has been taken for many decades now, and that is to identify close pairs of quasars and galaxies on the sky. So in this case, you always want the quasar to be in the background and the galaxy to be in the foreground. And in this particular instance, the galaxy is separated from the quasar by 50 kiloparsecs. So far beyond the extent of the stars in that galaxy, of course. And so if we rotate this image, in a manner of speaking, so we can look into the plane of the sky, if we take a spectrum of this quasar with our favorite telescope, then that spectrum will be sensitive to absorption in gas around this galaxy. And so what kinds of gas might we find in these environments? Well, of course, there's always gravity. And so we might find that some of these diffuse gas clouds that are sitting around in the intergalactic medium might be falling into this galaxy, and we might catch some of them on their way in. We might also observe some gas that used to be in the galaxy itself. And we know from observations like this one that galaxies can sometimes drive powerful outflows out of themselves. These outflows are driven by supernovae explosions, it's thought. And they can actually remove gas from galaxy disks, drive it up into the areas surrounding these galaxies. And so just to explain this image, this is an edge on galaxy. So here's the disk in white. And this galaxy is a starburst galaxy. It has a lot of star formation happening. And all of these associated supernovae are heating up the gas in the disk and driving it out. And so we're seeing that lit up in the X-ray in blue and in red in the H-alpha transition. So when we observe the gas around galaxies, we might very well be catching some of this material as well. So we're going to examine the diffuse baryons around galaxies, what I'll call the circumgalactic medium. And we're going to focus on an epoch very early in the universe at about redshift 2. This was an exciting time. Half the universe's stars formed between redshift 3 and 1. We expect that a lot of that star formation had to be fueled by a high rate of gas inflow, of course, and was probably associated with powerful gas outflows as well. So there's probably a lot happening in the circumgalactic medium at this particular epoch. So, in the past, people have generally focused on the gaseous environments around pretty bright galaxies because those are the easiest objects to find. So what's typically been done is to focus on, images of fields with very bright quasars in them, like this one. You always know you need a quasar, so it's good to start with that. And so people, such as these authors listed here, Adelberger, Steidel, Rudy, Crichton, etc., have imaged fields with very bright quasars, measured the colors of the galaxies in the image, selected those which are likely to be at redshift 2, and then did spectroscopic follow-up in order to confirm those galaxy redshifts. So in this case, this very impressive little blob here happens to be a bright star-forming galaxy at redshift 2. And its star formation rate is probably between 20 and 50 times the star formation rate of our own galaxy. And I'll refer to those galaxies as Lyman-break galaxies. So this is certainly possible. It's a little expensive because you're ending up trying to take spectra of really faint objects like this. But once you have the redshifts of these galaxies, you can then examine the quasar spectrum, calculate where you expect hydrogen to be, the Lyman alpha transition associated with the galaxy. It would end up somewhere over here. And then measure the hydrogen column density associated with that galaxy. And one can construct a plot like this: neutral hydrogen column density, just the surface density of neutral hydrogen along the line of sight, versus projected separation between the galaxy and the sight line. And so for this particular case, the sight line is separated by 80 kiloparsecs, and we can place a point on the plot right here. And so to further populate this plot, this figure, we need to collect many more pairs of galaxies and quasars. And Gwen Rudy has done this and populated the plot with about 50 measurements of neutral hydrogen column density around bright Lyman-break galaxies like the one in that image, to a separation of about 300 kiloparsecs. And this collection of data was assembled over many tens of nights of Keck time. So this is an expensive plot that you're looking at. And of course, Gwen Rudy has also examined the larger scale distribution of neutral hydrogen. So this, now we're zooming out of the halos. The x-axis here goes out to 300 kiloparsecs, and that's 300 kiloparsecs is here in this plot. Now we're looking at 3 megaparsecs versus hydrogen column density. Here's the average level of hydrogen absorption in the intergalactic medium. And you can see there's quite a bit of neutral hydrogen very close to these bright galaxies, but the level of neutral hydrogen absorption remains enhanced all the way out to 2 megaparsecs from these galaxies. So Lyman-break galaxies are indeed surrounded by a massive overdense hydrogen, well, yes, overdense circumgalactic medium. So we know about the hydrogen. What about the metals? We can learn about the metal absorption from the same spectrum. And this is just to demonstrate how beautiful these data can be. This is hydrogen absorption associated with a Lyman-break galaxy. This is relative velocity, zero velocity is at the redshift of that galaxy. But we can look at other ions in the spectrum. Of course, astronomers always mean, when we say metals, we mean any other element besides hydrogen or helium. And so oxygen, we call this a metal. This object has significant absorption from oxygen, magnesium 2, iron 2, this is singly ionized iron, singly ionized silicon, etc. And so now can collect these measurements and assess the median optical depth, or median surface density really, in a given transition versus transverse separation from the central Lyman-break galaxies. Pay attention to triply ionized carbon here. And you can see the absorption is enhanced in carbon-4 all the way out to about 2 megaparsecs, above the level observed in the ambient intergalactic medium. So not only are these reservoirs quite rich in hydrogen, but they're quite rich in warm carbon as well. So we've learned a lot about the environments of bright star-forming galaxies at redshift 2. Those galaxies look like this in this image. And I actually asked Richard Bouwens for some coordinates for this Lyman-break galaxy. So this is not just a random circle that I've put down here. This is a real galaxy at redshift 2. So this is the kind of galaxy environment that we've been studying so far, but there are so many other galaxies out there. This is one example. This is also a confirmed galaxy from Richard, a sub-L-star galaxy at redshift 2, and there are many, many, many more of those galaxies in this image. So the problem, though, with studying their environments is that they are very faint, and we never have this data quality around the very bright quasars that we need to study the CGM, circumgalactic medium. So instead of searching for these galaxies in emission, we search for them from their absorption signature. So if a galaxy's disk happens to lie right directly along the sight line to a bright background quasar, then it will give rise to a very strong neutral hydrogen absorption line in the quasar spectrum, and it will look something like this. This is called a damped Lyman alpha system, or a DLA. And the definition of a DLA is just that it has to have a neutral hydrogen column density greater than about 2 times 10 to the 20 particles per square centimeter. So if we see this kind of signature in our quasar spectrum, we know that the sight line is passing quite close to a galaxy's disk. Now, that galaxy probably has some gas clouds around it somewhere, and so if we know about another quasar, also in the background, but close to the first on the sky, then a spectrum of that quasar will tell us about the gas in this little galaxy's environment. Now, we will never know what these little galaxies look like, and I'm going to explain why. So people have studied, I tried to identify the emission counterparts of DLA host galaxies for many years with very mixed success. So this kind of demonstrates why that is, why this is so hard. This is the Lyman alpha absorption trough from a DLA. But these authors have identified this little blip of emission as arising from the host galaxy of that DLA. And it turns out that emission suggests the DLA has a star formation rate of about 10 solar masses per year. And even though it is actually forming stars at quite a good clip, the Lyman alpha emission is totally buried in the quasar trace in this spectrum. So that's why this is hard. On the other hand, though, sometimes DLAs turn out to be a bit brighter. This is another example of a quasar with a DLA observed along the sight line. And it turns out that this blob right here has the same redshift as that DLA, has a star formation rate of more like 30 solar masses per year. So when we select galaxies in this manner, we're probably getting galaxies over a wide range of luminosities. But on average, the galaxies are going to have much lower luminosities than Lyman-break objects. So what we need to do this then are some close pairs of quasars on the sky. And we may search Sloan and Boss imaging for these pairs. This is one example. Here are two quasars in a close pair here. They are at a redshift of 2.1 and have a projected separation of about 60 kiloparsecs. Here's a spectrum of the green quasar in the pair. You can see here's the DLA in the foreground at a redshift of 2. With associated metal line absorptions, also marked with the cyan lines. And here's the spectrum of the other quasar in the pair, which also is absorbed in Lyman alpha, as well as a few of these metal lines. So we are already observing the circumgalactic medium around a very likely very low mass galaxy with this one pair, a metal-enriched circumgalactic medium as well. And so it turns out that MAGE on the Magellan Clay telescope is the perfect telescope to do this experiment. So I've really enjoyed using it for that, for sure. And we've benefited from some time on other telescopes as well, and have collected a sample of about 40 of these quasar pairs with foreground DLAs, which we can use for this experiment. So now I'm showing you the average hydrogen absorption in the circumgalactic medium of these DLAs. So this is neutral hydrogen absorption strength versus projected separation from these systems. So here is actually the hydrogen absorption associated with the DLAs themselves at an impact parameter of 0. You can see DLAs have really strong Lyman alpha absorption by definition. And then the Lyman alpha profile drops off but is significant out to about 200 kiloparsecs from these galaxies. Now we can compare those measurements with what we know about the circumgalactic medium around Lyman-break galaxies. That's shown here in red stars. And we can also compare that to measurements of the halo absorption around galaxies which are host to very bright quasars. And that's shown with the blue symbols. Of course, those quasar host galaxies have halo masses which are much larger than either the DLAs or Lyman-break galaxies. So it appears that also corresponds to much stronger Lyman alpha absorption in the halo. But the main point here is that the absorption strength in the halos of DLAs and Lyman-break galaxies are basically the same. They're quite consistent, in spite of the fact that DLAs, we expect them to have much lower masses. And we can also compare these measurements with what we know about the circumgalactic medium at redshift 0. So these orange stars are Lyman alpha absorption strength measured around galaxies like our own Milky Way. You can see, again, the halo absorption is quite consistent between L-star galaxies at redshift 0 and L-star galaxies at redshift 2. The only environments which seem to have weaker halo absorption in the halos are those around dwarf galaxies at redshift 0, and that's shown with the green line, or the green symbols. So we're also sensitive to metals in these environments. Here I'm showing you the equivalent within carbon-4, warm carbon at about 10 to the 5 K, measured in individual pairs versus impact parameter. And you can see we're sensitive to we measure a wide range of carbon-4 absorption strengths, many weak systems, but also quite a few strong systems. And this is just a dividing line arbitrarily set at 0.2 angstroms. And here we're looking at absorption from cool silicon, so singly ionized silicon versus projected separation. Here is the 2 angstrom line, 0.2 angstrom line once again, and you can see we have many fewer strong silicon-2 absorption systems than we do strong carbon-4 absorption systems. So this cool photoionized metal-enriched material is a lot less common in the circumgalactic medium around these DLAs. Now, we can compute an incidence for these strong absorbers by simply counting up the number of measurements that we have out to, say, 100 kiloparsecs, and dividing the total number of systems with equivalent widths greater than 0.2 angstroms by that total number of measurements, and that is what I'm showing you here. So this is carbon-4 covering fraction. Warm and cool gas. You can see carbon-4 is again really common in these environments, whereas cool silicon-2 is a lot less common with a covering fraction of only 20%. Now we can use these measurements to get a handle on the actual amount of carbon in these environments. So we can pretend that the circumgalactic medium is just a sphere. Then the mass of carbon is simply given by pi times the radius of that sphere, the extent of carbon-4 squared, times the covering fraction of that carbon-4, times the fiducial column density of the carbon-4, the average column in the systems that we measure. And this is the mass of the carbon-4 atom, and this is the ionization fraction, or the fraction of the carbon that's actually in the carbon-4 state. And so we can use some numbers that we find from our analysis here, covering fraction of 50%, an extent of 100 kiloparsecs. We measure an average of about 10 to the 14 particles per square centimeter in carbon-4. And we adopt the most conservative possible ionization fraction for carbon-4. We adopt about 30%. It is not possible to have more carbon in carbon-4 than 30%. So when we do that, we find a total mass in carbon around the circumgalactic medium of these systems of about 5 times 10 to the 5 solar masses. Now we can compare that to the total amount of mass that we expect in carbon that we expect to be in the DLAs themselves. And to do that, we can assume a halo mass for the DLAs. Here I think I've assumed 10 to the 11.5 or so. Just to be conservative, that's a relatively high halo mass actually. And that suggests a stellar mass for the DLAs of about 2 times 10 to the 9 solar masses. We actually know the metallicity of DLAs really well from these absorption line measurements. We know that they're on average they have a metallicity of about minus 1.5. And so from that, we find that the DLAs, all the stars and ISM in these DLAs, contain about 3 times 10 to the 4 solar masses of carbon. And so you can see when we compare these numbers, the circumgalactic medium in these environments actually probably contains a lot more carbon than the DLAs, all of the star-forming regions in the DLAs themselves. So we can keep that in mind for later. And then finally, we can compare the metal line absorption strength in these various environments. So you saw this plot before. This is a comparison of Lyman alpha absorption between Lyman-break galaxies, DLAs, and quasar host halos. Here I'm showing you the amount of absorption measured in carbon-2, or cool carbon. DLAs are again in white. Lyman-break galaxies are again in red. You can see the DLA and Lyman-break galaxy halos absorb in the same strength in carbon-2 as well as in carbon-4. So it's been typically assumed for a while that the environments around bright star-forming galaxies are enriched by winds from the galaxies themselves. These bright star-forming galaxies have really high star formation rates, and perhaps their winds can eject metals to hundreds of kiloparsec distances from the central galaxies. But we feel that this is evidence that that process is not the dominant process that is enriching these galaxy environments, because we're seeing that these environments around galaxies, DLA host galaxies, which have very low star formation rates, have the same metal absorption strength as that around Lyman-break galaxies. The DLA galaxies, which have such low star formation rates, could not be driving all of these metals into their gaseous environments. And so we expect that this means that all of the carbon around DLAs must have been placed there by some other process. And perhaps even the carbon that we observe around Lyman-break galaxies as well. So we can get another hint about what might be going on here by looking more closely at the kinematics of these absorption lines. So here, the carbon-4 absorption transition is a doublet. There are 2 lines associated with it. And here, the magenta spectrum is the carbon-4 associated with one of our DLAs. And the white spectrum is the carbon-4 associated with the CGM measured at 70 kiloparsecs in projection from that DLA. And here, I hope you'll notice that these absorption lines have exactly the same velocity, even though they this gas is separated along these lines of sight by as many as 70 kiloparsecs. Now we can continue to look at another pair of DLA-CGM pair with strong carbon-4 absorption in both sight lines. And here, in this other example, the sight lines are separated by about 50 kiloparsecs. And of course, in detail, the line profiles are a little bit different, but the central velocity of these lines is about the same. And we can continue that experiment with all of the remaining pairs which have strong carbon-4 absorption in both the DLA and CGM sight lines. And we see that the velocities of this absorption are basically always the same. They're very similar to within about 100 kilometers per second. So this, we argue, evokes a filamentary structure for this carbon-4 absorbing material. We expect that if it were being driven out of galaxies by winds, that its kinematics would be much more complicated. But instead, this carbon-4 absorption has a quite quiescent kinematics and perhaps suggests that it was placed in the intergalactic medium at an earlier epoch, is now very peacefully falling into these overdense regions. Now, and there is even a suggestion that this carbon-4 could have been placed in the intergalactic medium at a much earlier epoch. And that comes from studies of galaxies around carbon-4 absorbers at redshift of 5. And so this is one such study from Diaz et al. The star here shows you a quasar sightline in which a strong carbon, and this is a redshift 6 quasar sightline, and Diaz have detected a carbon-4 absorption system along the sightline at a redshift of about 5. And then they have studied the distribution of galaxies around that sightline. So this is a distribution of Lyman-break galaxies. And this is a distribution of much lower mass, lower luminosity galaxies, Lyman alpha emitters. And they find that this carbon-4 systems are more than 10 co-moving megaparsecs from the main concentration of these bright Lyman-break galaxies that you see on the right here, on the left. And the closest Lyman-break galaxy is no closer than about 5 co-moving megaparsecs from this system. On the other hand, the carbon-4 is located much closer to the lower luminosity Lyman alpha emitters in this field. And so they're suggesting that this carbon-4 must have been placed there not by powerful Lyman-break galaxy winds at these earlier times, but perhaps was ejected into the intergalactic medium by much lower mass systems. So one way to try to understand how this process actually happens is to try to recreate it in a cosmological simulation. And that is the path that the Hernquist group has been pursuing to great effect here. And here I'm just showing you some results from the Illustris simulation. This is just to evoke the simulation, the distribution of dark matter that they start out with, and then the distribution of dark matter at redshift 2 in the simulation. And they've simulated a cosmic volume of 100 megaparsecs cubed here. And so Josh Suresh has studied the carbon-4 absorption strength around the simulated galaxies in Illustris. And here he's made a beautiful map of the column density of carbon-4 around one of the Lyman-break galaxies in the simulation. And then he's collected all of the measurements of carbon-4 together on this plot. Here's carbon-4 column density versus projected separation from those central Lyman-break galaxies. And Here he's showing us the results from many iterations of the simulation in which he's varied the feedback physics that he's implemented. He's varying the kind of galactic winds that the galaxies drive. So in the fiducial simulation, the carbon-4 drops down quite steeply. That's shown with the blue line. But if he includes faster winds at higher velocity, or if he heats the winds up, he's able to drive more carbon-4 into the circumgalactic medium of these objects at earlier times. But you can see that the observed carbon-4 column density around Lyman-break galaxies, shown with the purple points here, are still well above any of the predictions of the simulation. So it remains to be seen how feedback in galaxies is actually able to drive metals to these distances in galaxies at such early times. So in conclusion, we've learned that galaxies at redshift 2 are indeed surrounded by a very massive metal-enriched gas reservoir. Around Lyman-break galaxies, this reservoir extends to as many as 2 megaparsecs. And around DLA galaxies, that reservoir likely contains even more carbon, at least, than the star-forming regions associated with the galaxies themselves. The metals in these regions have quite quiescent kinematics. This carbon-4 gas that we've observed is extended, and so that suggests that it is distributed in a filamentary structure, maybe like the one that I tried to draw here, but maybe not. And then finally, the similarity between the metal absorption strength in the environments around both Lyman-break galaxies and around DLAs suggests that these environments are not enriched by ongoing winds, that they were enriched at an earlier time. And so it remains an open question how this enrichment actually occurred. And so there's lots more things to figure out, and that's all. Thank you.
The talk is now open for questions.
Are the winds always gravitationally unbound to the galaxies?
We don't know that. That's a very important question to answer. Most of the material is probably bound, but I think that question has not really been answered properly at high redshift, redshift 2.
Have any higher stages of ionization been observed, nitrogen 5, oxygen 6, and does that then constrain the energetics of the carbon-4, i.e. it must be photoionized?
Those transitions have been observed at low redshift, but they're very hard to observe at these redshifts because they're in the Lyman alpha forest. Right. So I think that analysis has not been done at these redshifts. But at lower redshifts, it has been done, and the thing is there probably are multiple phases for the gas. I think that's the main finding. Oxygen 6 is associated with collisionally ionized material, but carbon-4 and the lower ions probably are in a different phase. Yeah.
Have you ruled out the effect of tidal interactions?
In drawing the metals out of the gas, I think they certainly could have. Absolutely, no, not at all. That could certainly be an important process, but there's no way to distinguish that at very early times that I'm aware of.
Another question: when you compared your carbon-4 column densities with the illustrious simulations. It looked like the issue was that there was enough carbon-4 in the entire simulation. It was just getting it out to the great distances that was the issue. Is that the concern?
I think that generally is the correct interpretation. Isn't that right?
Yeah, that is the problem.
Yeah.
Because these are considerable distances over relatively short periods of time.
Yeah, so the faster winds model, the reason it works better is because the winds are able to escape the halo at early times. And so the metals that you see out there at 200 kiloparsecs have been there for a long time. Okay. And the slower winds models, the metals are, if any metals are out there, it's because of AGN activity at late times.
So the key is to get more metals out into the IGM, I guess,
Right, at
the
earliest
times.
Exactly.
Do you have any other questions? Yes, Bill.
In the previous slide you compared to a whole bunch of different models over there. And so one common one was no AGN. Do other ones have AGN in the model?
Yes, I think most of the other ones do have
the
AGN.
Okay, and even the AGN still don't make it flat enough,
They
essentially.
don't do enough, but I guess they are just really turning on at this apex, so they haven't really had that much time to have an impact in the simulation.
In this particular simulation. So the principle of one could have turned AGN on earlier.
You could. Would that be justified, do you think? Yeah, okay. Quasars at redshift 7. Maybe we should be turning AGN off at earlier times.
It's also more of an issue for the DLAs because even if you can turn on AGN for the massive galaxies that we looked at here, they probably aren't doing much for the DLAs.
Yeah,
so.
that's a good point.
Okay. Oh, go ahead.
Is this the highest redshift that you can make this comparison with? Or you can go even up beyond 5?
The observations just don't exist yet beyond a redshift of 2.5 because it's so hard to find the galaxies at that time. But I think actually with JWST, that's what we'll have to use to find very high redshift galaxies around, these redshift 5 quasars or redshift 6 quasars.
Zach?
Can you go back to the plot where you show the relative velocity speed?
Yeah.
0 between all those? So how many pairs of objects are actually behind this? Like, is this all of them that you have, and is each of these panels one pair?
This is all the objects. So I guess all the 12 objects where we detect strong carbon in both the CGM and DLA sightlines.
So is it just based on these 12 objects that the conclusion that winds aren't important is coming?
Well, this particular claim about the quiescence of the absorption, yes, it's just based on these 12 objects.
And do you have some quantitative measure for how sort of significant the lack of difference between the velocity actually is in each of these? Because, for instance, in that one on the second sort of rightmost column, the second one from the top, it's kind of hard to see that there's any line up in the...
They don't lie all on top of each other, but they're never more than 100 kilometers per second apart. And people claim that Lyman-break galaxy winds have velocities extending out to 800 kilometers per second. So I would expect, if these were arising from winds, the winds would, get something much more complex.
Okay then. Let's thank our speaker again.